Welcome back. Let's talk about the effect of the derivative on the shape of the graph, section 3.3. First, let's focus on the increasing and decreasing test. Increasing and decreasing test uses the derivative to exploit the behavior of the graph, behavior of a function. So let's assume you have a graph. You have the graph of f of x. Here is f of x. Somehow it looks like this. Y equal to f of x. If you look at the derivative at this point, for example, here's the tangent line. The derivative at that point x is basically the slope of the tangent line at that point. If you look at the tangent line seems to be increasing line, so it means the slope must be a positive number. If you pick any other point, you will still see slope is positive. On the other side, if you look at the point here, call it x2 or something, you look at the slope of the tangent line, slope here is negative, means the derivative at the point x2 must be negative. This is referring to the fact that on the left side of whatever this point is c, on the right side you have a decreasing function, means the slope of the tangent line at that point, at any point on this graph, would be decreasing. It would be negative because the corresponding slope of the tangent line is the same as the derivative at that point. So the derivative would be negative, which means the function would be decreasing. On the other side, if the function is increasing, the slope would be positive. If you relate these two, then we can say the increasing and decreasing test is basically looking at the corresponding sign for the derivative. If the derivative is positive at this point, on a specific interval, then that interval, the value of the function on that interval is increasing. If you look at the derivative on an interval and say the derivative there is negative, then the value of the function is decreasing on that interval. Okay, this is nothing too complicated as long as you look at the graph and see, okay, if I have an increasing part and the slope of the tangent line are just positive, and if I have a decreasing part, then the slope would be, tangent line would be negative. How about this point? You look at the tangent line at that point. What do we know about the slope? The slope is 0 there. And what do we know about this point? We call it x. We know the derivative at the point x is 0. This is what we called the other last time. We called it critical number. Critical number. So we have a critical number where the derivative is 0 or the derivative is undefined. Maybe it's a breakpoint or something like absolute value. This is a breakpoint. Okay, so let's focus on this property to discuss the behavior of the function or increasing and decreasing interval. So here's an example. How do we find the increasing and decreasing interval? Instead of solving the inequality, we're going to just figure out what is the sign for the derivative function. So we're going to discuss something called the chart sign of the f prime. First, you need to figure out what is the critical what are the critical numbers. So first, figure out what is f prime x. Be 3x squared minus 6x minus 9. This is the f prime. To find the critical number, you should say, I'm going to set the derivative equal to 0 or find out whether the derivative does not exist. In this case, the polynomial is well defined, so the derivative always exists. You can factor out the 3. You can factor this polynomial into x minus 3 and x plus 1. So there are two solutions. Either x is 3 or x is negative 1. These are the two critical numbers. I draw a number line. This number line is what we call it the sign chart for f prime. This is for f prime. It's very important that you draw this number line. 3, negative 1. These are the critical numbers, 3 and negative 1. And instead of solving the inequalities to see where the derivative is positive, where the derivative is negative, to discuss the increasing and decreasing interval, we pick test points. How you solve the inequalities are normally through test points as well. In each section, these critical numbers break down the number line into sections. In each section, pick a test point. I'll pick -2 here. I'll pick 0. I'll pick 5. These are the test points. Then I'm going to try test points for what? For f prime. That's why I wrote this. This sign chart is for f prime. That means try these numbers into the f prime. At -1, by the way, f prime must be 0 because it's a critical number. The same as at 3, the derivative must be 0. That's how we found these two. We said where the derivative is 0. If it at 3 was a point where the derivative does not exist, I would write does not exist. In this case, these 2 points, the derivative is 0. Test points for those -2, 0, and 5. Let's find out what is the derivative at -2, derivative at 0, derivative at 5. I want to find out values of derivative at that. If you replace -2 into the function derivative here, what do you get is 12, 12, 24 minus 9, 13, or 15. If you replace 0, you get -9. If you replace 5, that's 25, 75. I don't know why I picked such a large number. Actually, this would be faster. 5 minus 3 is 2. 5 plus 1 is 6. 6 times 2 times 3. 36. Okay, so the derivative would be, the value would be 36. So you can check these values, doesn't really matter. What matters is the sign. Here 15 is a positive number. So correspond to -2, I found the derivative is 15. So 15 is a positive number. Derivative of 0, at 0 was -9. So here, negative number I got for 0. For 5, I got derivative to be positive. These signs basically tell you what are the derivatives in each section. In this area, the derivative is always positive. In this section, the derivative is always negative. In this area, the derivative is always positive. And what does the derivative tell you? Through the increasing and decreasing test, look at the increasing and decreasing. Because if the derivative is positive, that means the function is increasing. F is increasing if the derivative is positive. If the derivative is negative, then f is decreasing. So here I found out that f prime, if the derivative, so f prime is positive, means the function is increasing. F prime is not increasing, the function is increasing. F prime is positive. Here f prime is negative, the function is decreasing. And here is f prime is positive, function is increasing. Okay, so if I ask you where is the increasing and decreasing interval, increasing interval would be from -infinity to -1, as well as from 3 to positive infinity. Now, a decreasing interval, it happens to be at -1 to 3. So in this area, the function is decreasing. Everywhere else, the function is increasing. And you can sketch the graph somehow. Let me try to give you a sketch how it looks like. The function is increasing first, up to on x and y axis maybe. Here. Let's look at the function. It says the function is increasing up to -1. So here's -1. Function is increasing up to here. At -1, it decided to change direction. It means the function starts to decrease. Goes the other way. Up to where? Up to x value of 3. At 3, the function decides to go increasing again. And there is no coming back since always increasing after that. So you have to create a smooth transition since the derivative exists always. So you get this graph. This is the graph. It's not exactly at these points, but the increasing and decreasing points happens to be at -1 and 3, where the change happens. And if I ask you at this point, Where's the local maximum? And local minimum, you should be able to answer it based on the graph. Local maximum happens at -1. Local minimum happens at 3. We can extract this information through this sign chart. Means the function was increasing, then the function turns into decreasing. What happens at this point is you connect an increasing to decreasing. That means you create a local maximum. If the function is decreasing, then turn into increasing. Means at the point 3, there would be a local minimum. Otherwise, at the point -1, you have a local maximum. This information comes out the chart, the sign chart as well. Increasing to decreasing, that means change from plus sign to negative sign. Plus sign, it represents increasing, negative sign represents decreasing. That happens, you have a local maximum. And the other side, if you go from negative to positive, you would have a local minimum. If it's positive to positive or negative to negative, there is no local maximum mean in between. So here's what we call it, the derivative test, the first derivative test. You find the local maximum or local minimum. If you have a critical number, in our case, you had -1 and 3, the example. And if f prime changes sign from positive to negative means from increasing to decreasing, then the point in between is the critical number. That point is the local maximum. On the other side, if the derivative changes from negative to positive, that means the function changes from being increasing to decreasing, then the point in between, that is a local minimum. And that point in between, we call it C or whatever. Okay, so the derivative and that specific sign chart tells you a lot about how the function behaves, where is the local maximum and minimum. Here's an example. Find the local maximum and minimum for the function g of x equals x plus 2 sine x over a specific interval 0 to 2 pi. So let's try to do that. First, you find the critical numbers. G prime x would be 1 plus 2 cosine x. Critical number happens to be where the derivative is 0 in this case. 1 plus 2 cosine x equal to 0. This is to find the critical number. First, you need to figure out the critical number. Means cosine x equals -1/2. If you use the unit circle, cosine happens to be, this is not a circle. Cosine happens to be -1/2 at these two specific locations. This angle as well as this angle. But since the interval is given 0 to 2 pi, you should write the angles in between 0 to 2 pi. This is one of the answers. The other one is from 0 to, I think it's 4 pi third. So either the angles are 2 pi third, that's one of the answers. The other one is 4 pi third. Okay, you can write the angles, you can represent the solution in another way as well, but this specific interval restricts you to write it only in this way. Okay, so we found the critical numbers. I need to draw the number line. Here's the number line. The number line is for the first derivative. Write the first derivative next to it, since later on we will have the second derivative as well. We'll discuss behavior of the function based on the second derivative as well. The interval given is 0 to 2 pi. So I'm gonna make sure that whatever value I pick as a test point is between 0 to 2 pi. The critical numbers, 2 pi third and 4 pi third. Okay, this is a critical number. The derivative there is 0. The derivative here is 0. This is representing the derivative. Pick test point. Test point here between 0 to 2 pi third. This is 0. This is 2 pi third. I'll pick this point here, angle pi half. I'll pick pi half. Between 2 pi third and 4 pi third, you can pick pi. And here I'll pick 3 pi half. These numbers that I pick correspond to these three locations. between 0 to 2 pi third and 2 pi third to 4 pi third, as well as 4 pi third to 2 pi. I cannot go beyond that since the interval is given specifically 0 to 2 pi. Okay, replace these test points into the derivative function, into the g prime. If you replace pi half, what you get is 1 plus 2 cosine of pi half is 0, so you'll get 1. That means the derivative is positive. If you replace pi, you'll get negative 1, so that means the derivative is negative. And if you replace 3 pi half, you'll get positive number again. It's the sign that matters, not the value. The sign means the function is increasing. This one means the function is decreasing. And here, the function is increasing. So what are the increasing and decreasing interval? Even though the question did not ask for it, but I want you to see increasing, decreasing interval. Increasing is from 0 to 2 pi third. Union 4 pi third to 2 pi. And decreasing is from 2 pi third to 4 pi third. By the way, this is not always alternating plus minus plus. That's not the case. You could have plus 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 as well. You could have minus minus plus. Those are all possibilities. It's just that the fact that these functions are very simple, the derivative alternates. Okay, so we found these, and the question was find the local max and mean. What is the local max? What is the local mean in this case? The local maximum is when the derivative changes from positive to negative. That means this point here is a local maximum. This is where the local maximum happens. The derivative changes from positive to negative. That means the critical number 2 pi third is corresponding to the local maximum. On the other side, when the derivative changes from negative to positive, here's the local minimum. If you draw these arrows, it kind of tells you the shape of the graph. You expect to go up, then down, then up. So what you have here is a local max. What you have here is a local min. Okay. Just make sure that you do not mix it up with these test points. The test points are kind of useless. After you figure out the sign, these test points are useless. You shouldn't mix it with those. Use a different color for the test point so you do not mix it. Okay, so we found local max and local mean. They ask you for local max and local mean value. That means find their corresponding y value. If they say local max value, if they ask you for the point, you should write 2 pi third as the x coordinate and the y coordinate, which whatever the y coordinate is. So let me write it as a point. It would be 2 pi third. And the corresponding y value, where do you get the y value is from the original function, always gives you the y value. Here's where the y value comes from. It doesn't come from the derivative. Don't go to the derivative. It comes from the original function. So replace 2 pi third into the original function. What you get is 2 pi third plus 2 times sine of 2 pi third, which is root 3 over 2. You can simplify it to 2 pi third plus root 3. And you can find local minimum. Similarly, it would be if you replace 4 pi third into the function, be 4 pi third minus root 3. So we found the local max and mean. If they want the value, you only type in the y value. You only type in these two. If they want the point, you write the x and y coordinate. Okay, so kind of you can expect how the graph looks like, by the way, as well. If you find these numbers decimal, you can find the graph kind of precisely. But let's see. You graph the function over the interval 0 to 2 pi. Starts from 0. If you replace 0 into the function, turns out you get 0. So you start from here. The function increases up to 2 pi third. The y value is this guy, star. And it starts to decrease up to 4 pi third. This y value here, call it box, is this number, 4 pi third minus root 3. Then the function starts to increase again, 2 pi. We start at 2 pi since the interval given 2 pi. You see here you have a local minimum and local maximum. The endpoints could be absolute max and absolute mean, but you have to calculate their y values and compare which y value is larger, which y value is smaller. I didn't use calculator to find the decimal values. I'm guessing that the endpoints are going to be larger. Okay, so here, this is not the end of this section, but I'm going to break up the subject into two parts. One is the first derivative, then we're going to discuss the second derivative property on the graph for graphing a function and behavior of the function. I'm going to stop at this point.